Okay, so in the chapter 15 practice, the first one says identify each of the following as an Arrhenius acid or Arrhenius base. Write the equation of the substance when placed in water. So let's review the definition. An acid is a substance that produces H3O plus in water. And a base is a substance that produces OH minus in water. Now, in general, the formula of an acid is going to have a hydrogen somewhere in it, and normally it's either going to be in the front of the formula or after a COOH, which is this H that's acidic, and that's called a carboxylic acid. Now, a base normally is a metal plus a hydroxide ion, so for example, a metal like potassium with hydroxide. And when that's placed in water, it dissociates. Other bases like ammonia, can react with water to form hydroxide ions. So let's identify them first, and then we will write the reaction. Okay, so letter A, the first thing my eye goes to is this COOH, which is a carboxylic acid, as I showed you above, and so this is an acid. On letter B, I go right to seeing this H2 in the front of the formula, and this is an acid. Letter C is a metal with a hydroxide. There's my hydroxide. The lithium is my metal, and that's the definition of a base. And then NH3 is ammonia. Ammonia is also a base. So now let's go back and write the reactions of these with water. So an acid, here's my acid, is going to donate a proton. Now in the carboxylic acids, it's this proton right here that's going to be donated. So you take the acid, you add it to water. This reaction happens to be a reversible reaction because it's a weak acid. We didn't really go over that too much. I'm going to include the double arrows here, but if you had just written a straightforward arrow, that would be okay. But this hydrogen here is going to come off and go to the water. So we would get CH3COO. I'm taking off an H plus, so that leaves that with a negative. And then the H plus goes to the water, and I get H3O plus. Now, acids like the sulfuric acid here, it's this hydrogen here in the front that comes off. So if you notice, in both cases, the acid have a proton or an H plus that come off in the solution. So in this case, I write my acid. I'm placing it in water because that's the requirement of an Arrhenius acid. This sulfuric acid is a strong acid, so it has a straightforward arrow. Now I'm going to take one of the hydrogens off, and it's going to go to the water, actually the H plus. So I have HSO4 left with a negative, and then the H plus goes to the water, and it's H3O plus. Now for bases, when it's a metal and a hydroxide, remember that metal ionic compounds, when you place them in water, dissociate. So the LiOH is not really reacting with water, it's just being placed in water, and it will dissociate into lithium ions and hydroxide ions. Now ammonia is an example that reacts with water, and I've really only asked you to remember ammonia. And so what happens is the hydrogen, the H plus in the water, will react and go to the ammonia. So then ammonia becomes NH4 plus, and then the water is left with OH minus. And I was just looking up above. This is not a plus, that's a minus. Okay, so that's how we identify areneous acids or bases, and look at the commonality or the things that they have in common in what the acids do in water and then what the bases do in water. Now, when you are, these second definitions here, or the second question number 2 here, draw the conjugate acid of each base. And then number 3 is a conjugate base of each acid. These two words here have to do not with the Arrhenius definition, but with the Bronsted-Lowry definition. Now, Bronsted-Lowry definition, the acid is a proton donor, and the base is a proton acceptor. And so in the Bronsted-Lowry definition, the acid and base reaction occurs in one equation. It's not two separate reactions, it's one equation. And when we talk about the conjugate acid or the conjugate base, we're talking about the species that the acid or base makes when, if it's an acid, it donates the proton, or when it's a base, it accepts the proton. So if I'm looking at this second question, it says draw the conjugate acid of each base. Okay, so this, what they've given me is a base. And if you look at the definition, what a base does is it's going to add an H+. Okay, so if I want to know what the conjugate acid or what the base will look like when it adds the H+, then I'll take the formula that's given and add H+. So a Br-, I would add an H to it. And then looking at the charges, it has a minus. If I add a plus to that, it would cancel and it would be neutral. Now a CO3 2-. So I'll add a hydrogen to the formula because that's what a base is going to do. Now it's a 2-, so I'm going to add a plus to that. And so instead of having a 2- now, I would have a 1-. So these two here are the conjugate acids of the bases. So if I was looking at this in an equation, the base would be on the reactant side on the left, and then the conjugate acid would be on the product side on the right. So now let's take a look at question 3, which is similar, except this time they've given us the acids, and they want us to draw or write the conjugate bases. So I know that acids donate protons, so I'm going to say minus H+. So from the formula, I'm going to take away an H+, and that would give me my conjugate base. So if I have NH4+, and I take away a hydrogen, I would have NH3. Now look at the charge, it has a plus, but I'm removing a plus, so then it would go back to neutral. Now HPO4 2-, so if I look at the formula and I take away an H, I have PO4. I'm also taking away a plus, and every time you take away a plus, you leave another negative behind. So I had 2 negatives, but now I'm going to have 3 negatives because I took away an H+. I think in question 5, they ask you to label an equation, and so we'll practice this again. Now question 4 wants us to define strong and weak acids. And so a strong acid is any acid, and it actually would also be for bases, but a strong acid which ionizes or dissociates 100%. which means it goes to completely make products. So 100%. And if you look in your book, there's actually a short list of acids and bases in water that will be considered strong acids or dissociate 100%. So strong acids are only a short list. It means that we have a lot more what we call weak acids. And weak bases would have a similar definition. So strong acids are 100%. Well, anything that doesn't ionize or dissociate 100% is called a weak acid. So we would say that it just partially dissociates or ionizes. Now this is where on the weak acids were those back and forth arrows that we had that I wrote in problem 1. Because if you only partially ionize or dissociate, it means you're only partially making products. That means if I were able to look into the beaker and see what was there, there would not only be products. Some of the reactants would remain because I can only partially ionize or dissociate to make products. So let's look back at question number 5, or let's think of question number 5 has us label the conjugate acid-base pairs. So in this case, they've on questions 2 and 3, we were given acids and bases and asked to predict what they would look like. In question number 5, we're given a reaction, an acid-base reaction, and this acid-base reaction is from the Bronsted-Lowry definition. And so here we have to, in the equation, identify the acid, which is the proton donor, remember, and that's the H+, the base, which is the proton acceptor, and then their partners, so the conjugate base and the conjugate acid, which would be on the product side. On the product side. Okay, so what I always kind of, at least visually in my mind, I connect the partners. Right, so I look and I see the only thing that should be changing in these reactions is the movement of a hydrogen H+ from one reactant to another. So I see that if I look at my chlorine here, I see that I compare it here, and I see that it added or accepted an H, because it did not have an H on the reactant side, and now it does on the product side. Well, that means that chlorine is acting as a base because it accepted an H+. And the species that became, once it accepted the H+, would be called its conjugate acid. And so that is a conjugate acid-base pair. That's the base with its partner, its conjugate acid. Now automatically the HSO4- would have to be the acid, because you have to have an acid and a base on the reactant side. But looking, if I look here at HSO4- and compare it to SO4-2-, I see that it has lost its H+, or donated it, so that would fit the definition of an acid. When HSO4- donates its H+, its partner on the other side becomes SO4-2-, and that is the conjugate base. So now we want to indicate, on question 6, it asks us to indicate whether the things are acidic, basic, or neutral. And so let's think about it in terms of pH. So I know I'm going to write on the bottom a pH that is equal to 7 is neutral. A pH that is greater than 7 is basic, and a pH that is less than 7 is acidic. So right away I can label this one as acidic. The 7.5 is slightly basic, 13.5 is basic, 7 is neutral. Now the other two are in acid concentrations, and we could use acid concentrations to identify this, but I think it might be easier to do pH. So I know that pH equals the negative log of the acid concentration, which would be the negative log of 3.16 times 10 to the negative 2. So plugging that into my calculator, let me do that. I get 1.500. So this is an acidic solution. And you may say, well, why did you keep writing all those zeros? Which would be a good question. It's the rule that we use for pH and logarithms and to know how many decimals. The number of digits in the coefficient, so see there's 3 digits in the concentration coefficient, that's how many places you write your decimal to. On an exam, I would not be super strict about this, but if you're doing homework or working in the book and seeing an answer, you may see this. So 3 places in the coefficient corresponds to 3 decimal places in the pH. Okay, the other one is down here, and do you remember if there's a 1 here, that the pH is equal to the positive value of the exponent? So in this case, I wouldn't even plug it in. The pH would be equal to 4, and this is acidic. You can test it for yourself, though, if you just plug it in to negative log of 1 times 10 to the negative 4, then you would get the answer 4. Now, number 9 says define electrolyte and non-electrolyte. An electrolyte is a solution that conducts electricity because it has ions. There are 3 types of substances that are electrolytes: acids, bases, and soluble, which means they dissolve, salts, which a salt, remember, is the generic word for an ionic compound. Now, if you put the word non in front of the word electrolyte, if electrolytes conduct electricity, then these do not conduct electricity. And if they were conducting electricity because they have ions, non-electrolytes do not conduct electricity because they do not have ions. Now, common things that are non-electrolytes are covalent compounds that are soluble in water. Things like sugar would be an example. Sugar is C6H12, or glucose is O6, and that is all covalent compounds that would not dissociate to form ions. You could have other things like an alcohol, CH3. Methanol would be CH3OH. This has all covalent compounds, and so when they dissolve, they do not dissociate.